Right. So is it visible to you?
Yes, sir. Yes.
Yeah, yeah. Yes. Okay. Yes. Right. Right. Is it visible?
Yes, sir.
Right. Right. D by Haeckel theory. So as we discussed previously, so there are some assumptions of the D by Haeckel theory. So what are those D by Haeckel theory assumptions? We'll see. Okay. Right. Generally, we discussed that the strong electrolytes, here strength is there. Strong electrolytes are completely dissociates into the ions, and the weak electrolytes are partially dissociates into the ions. Right. Then the strong electrolyte solutions are having the high dielectric constant values due to electrostatic attractions between the ions is small. Strong ions means that is positive and negative ions distance will be very small. In between these two distances, it is a very small distance will be there, right? So between these two ions, a small distance will be there. That's why these are strong electrolytes. These strong electrolytes are having high dielectric constant values. In case of weak electrolytes are dilute solutions, right? The electrostatic attraction between the ions is strong, and in this causes low dielectric constant values because of the long distance between the ions, right? This is the positive ion and this is the negative ion. The distance between these two ions is too far, right? The distance between these two ions is too far, right? So this is the differences between the strong electrolytes and weak electrolytes. So based on dielectric constant values, right? And dissociation nature. Okay, right. So from the Newton's law, the force of attraction, between the ions is directly proportional to the product of the charges, and it is universally proportional to the distance, the square of the distance between them. As force of attraction, F is directly proportional to Q1 into Q2 by R square, right? Right. Then, so one more assumption, that is in electrolyte solutions, each ion which is surrounded with many number of opposite charged ions in a symmetrical manner. That means if it is a cation, that cation is surrounded with many number of negative ions. The cation is surrounded with many number of negative ions. And the negative ion is surrounded with many number of positive ions. That surrounding nature is in symmetrical environment. Symmetrical environment. So once we applied the electric field, that symmetrical environment may be disappear and asymmetrical environment may be appears, right? So that we'll see. Right. So this is the term interionic effect, that can be explained with the help of two parameters. One is the asymmetric effect or electrophoric effect. So this asymmetric effect is sometimes is known as relaxation effect. Asymmetric effect is known as relaxation effect, right? So what is the asymmetric effect? We'll see, right? So the asymmetric effect means, so this is the asymmetric effect, right? The asymmetric effect means this is the central positive ion which is surrounded with many number of negatively charged ions in a symmetrical environment. Symmetrical environment means symmetrical manner. So this is in the absence of application of electric field. So once the electric field is applied, that is positive pole and negative pole will be there. So these all positive ions are moves towards their negative pole and the negative ions are moves towards their positive pole. So due to movement of these ions, the symmetrical manner will be disappears. Therefore, asymmetrical environment is appears. So there is a asymmetrical environment, right? So when this asymmetrical environment is there, right? So what will happen? Okay, right. See, in electrolyte solution, the central positive and negative ions are surrounded with many number of opposite charged ions in a symmetrical manner. So that I already know. So when we applied the external current to the electrolyte solution, the central positive ion moves towards the negative pole and the central negative ions moves towards the positive poles, right? So that means the central ions and surrounding ions are moves towards their opposite charged poles, right? Which causes the destroying the symmetrical environment of central positive ion, which leads to decreasing the mobility of the central ion, right? So once the central ion that will be moves towards the opposite charged pole, the remaining surrounding ions which retards the mobility of that central ion, right? Which retards the mobility of the central ion. Such effect is known as asymmetric effect, right? So, and the electrical conductance of an electrolyte solution is decreases. Finally, with the help of a symmetric effect, the conductivity of the central ion will be decreases because of the attraction of opposite charged electrons, right? So which retards the mobility of the central ion, which will move towards the opposite charged pole, right? And we start the electric field, right? So the time which is taken for conversion of asymmetrical environment to the symmetrical environment, which is known as relaxation time. And this phenomenon is known as asymmetric effect or relaxation effect. Asymmetric effect or relaxation effect, right? So one more will be there, that is electrophoretic effect. Electrophoretic effect. So what is the meaning of electrophoretic effect means? For example, if we consider the central ion is the positive ion, this positive ion is the central ion, right? So this central ion is surrounded with water molecules. If we can use water is the solvent, all water molecules are surrounded by this central ion, right? All the water molecules are surrounded by the central ion. The size of the central ion will be increases. The size of the central ion will be increases. Therefore, size is increases means its mobility is decreases. Size is increases means its mobility is decreases. Therefore, in this case also, the electrical conductivity of the solution is decreases. Therefore, such effect is known as electrophoretic effect, right? So see, in addition to the asymmetric effect, the mobility of the central ion is decreases due to the solvent molecules are surrounded with the central ion. So due to solvent molecules, these solvent molecules, right? So the solvent is the water molecule. So once the water molecule is surrounded with the central ion, right? So if the solvent water molecules, many number of hydrated molecules are surrounded with the central ion, which leads to the retarding the mobility of the central ion, which makes towards their opposite pole, right? So which causes decreasing the electrical conductance of an electrolyte solution. So such effect is known as electrophoretic effect, right? So simply by deposition of water molecules on the central positive ion or negative ion, right? So positive ion will be there means oxygen will be connected, right? So water means H2O, right? H2O, the oxygen will be connected to the central positive ion. So these are the hydrogens. If it is a negative ion, hydrogens will be attached to the central negative ion. So due to these, many number of water molecules are depositing on the central ion. So at that time, the mobility of that central ion will be decreases. So in this case also, mobility of the central ion is decreases. Therefore, the electrical conductance also decreases. These two effects are asymmetric effect or electrophoretic effect. So which explains the retarding the mobility and the decreasing the electrical conductivity of an electrolyte solutions. Is it clear?
Sir.
Yes. So coming to the one more topic, that is D by Heckel limiting law. D by Heckel limiting law. So with the help of assumptions of D by and Heckel, right? So this is the D by Heckel limiting law. So what they explained about the asymmetric effect and electrophoretic effect, asymmetric effect and electrophoretic effect. With the help of that two concepts, Debye and Haeckel derived one equation, that is Debye-Haeckel limiting law. Debye-Haeckel limiting law. So what is the Debye-Haeckel limiting law? How it should be applicable for the electrolyte solutions, that we'll see. Right. The Debye-Haeckel limiting law is applicable for only weak electrolytes. Only weak electrolytes. For strong electrolytes, it is not applicable. Strong electrolytes are completely dissociates into the ions. Strong electrolytes are completely dissociates into the ions. Weak electrolytes are partially dissociates into the ions. Therefore, the Debye-Haeckel limiting law is applicable for weak electrolytes only. Right? In case of weak or diluted electrolyte solutions, which are deviated from the ideal behavior, right? So generally that weak electrolytes are partially dissociates into the ions, and those weak electrolytes are deviating from ideal behavior, deviating from ideal behavior. And also, according to the, right, and also according to the D by Haeckel theory, right? According to the D by Haeckel theory, so the D by Haeckel limiting law can be expressed as in this form. That is ln gamma plus or minus is equals to minus 1.825 into 10 to the power of 6 z plus z minus modulus by dt power 3 by 2 into square root of I, right? So the derivation derivation of d by Heckel is not required, right? So d by Heckel limiting law directly we have to remember. So that is, even in the syllabus is mentioned, there is no derivation for d by Heckel theory, but d by Heckel Onsager derivation will be there, right? How it will come this equation? So derivation is no need. We have to remember this equation with the help of assumptions of asymmetric effect and electrophoretic effect, right? So d by and Heckel derived this equation that is called d by Heckel limiting law. D by Heckel limiting law. Okay, right. So once again we will see this equation. Ln of gamma plus or minus ln of gamma plus or minus is equals to minus 1.825 into 10 to the power of 6 modulus of z plus z minus. This is the product, right? So z plus means positive ion charge. We have to write in the suffix z plus and into z minus. Z plus into z minus. That is the modulus of z plus into z minus. Modulus of z plus into z minus. Okay. Divided by dt power 3 by 2 into square root of I. So what are those parameters? We'll see. Right? Here, right. Gamma plus or minus means mean ionic activity coefficient. This is discussed in activity concept and activity coefficient concept. Plus or minus whenever both ions we are representing, that may be expressed with mean concept, that is mean ionic activity coefficient. Z plus means charges of the ions, positive ion, Z minus is the charge of the negative ion. So Z plus and Z minus. Z plus and Z minus are the charges of ions of an electrolyte solutions. Then D is the dielectric constant of an electrolyte solution. T is the temperature. Then I is the ionic strength. So this is the concept. Ionic strength concept is more important for exam point of view, right? So that we'll discuss, right? So at 25 degrees centigrade, the above equation can be modified and can be written as, right? These all are parameters. So at 25 degrees centigrade, the d by Heckel limiting law equation can be written as ln gamma plus or minus is equals to minus a of z plus z minus into square root of I. So a value that is some constant that is 0.0591, right? This is applicable for the water at 25 degrees centigrade. Therefore, ln gamma plus or minus is equals to minus a of z plus z minus into square root of I. What is the ionic strength, right? So whenever the electrolyte solutions will be there, right? So what is the ionic strength? The concept of ionic strength we'll see. So the ionic strength definition, right? Is it visible?
Sir,
Yes. Is it visible ionic strength?
Sir,
Yes, yes. Yes, tell me. Okay. Right. What is ionic strength means that we can explain with the help of this simple equation. That is I is equals to 1 by 2 of summation NiCi Zi square. of summation NiCi Zi square. This is the definition only. Just see. Ionic strength of an electrolyte solution is defined as half of the means 1 by 2. Here I am writing half of the means that is the 1 by 2. Half after half, the sum means that is the summation. Half of the sum of the product of number of moles of ions, that is the Ni. The product of number of moles of ions, Ni, then concentration of the ions, that is the Ci, and square of the charges of the ions, that is the Zi square. Zi square. This is the ionic strength. Half of the sum of the products of number of moles and concentration of ions and square of the charges of the ions, right? So that is called ionic strength. Ionic strength, right? Simple with the help of this equation. So any one equation will be there. So that is, for example, KCl is an electrolyte solution. So this KCl is an electrolyte solution. This KCl will be converted into the K plus and Cl minus ions. That is the K plus and Cl minus ions. What are the number of moles of K plus? If 1 mole of KCl is dissociated into the K plus and Cl minus, the number of moles of K plus is 1. The number of moles of Cl minus is 1. Okay. Number of moles. And what is the concentration of the K plus and Cl minus means? The same concentration as the KCl does have. So that will be same for K plus and Cl minus. K plus and Cl minus. And charge of K, that is the +1, and the charge of Cl, that is the -1. So the square of these charges, the product of all those things, that will get the ionic strength. That will get the ionic strength. Okay. Simple, the ionic strength I is equals to half of the summation NiCi Zi square. Ni is the number of moles of the ions, Ci is the concentration, Zi is the charge. If two ions will be there, any electrolyte solution that will be dissociates into the two ions, right? So each ion individually we have to consider. So that is, if for univalent electrolyte solutions means one positive ion and one negative ion will be there. So for that ionic strength I is equals to 1 by Z of, this is belongs to cation and this is belongs to anion. That is C1N1 Z1 square plus C2N2 Z2 square. So any electrolyte solution will be there, two ions will be there. So that two ions individually we have to consider, that is half of C1N1 Z1 square plus C2N2 Z2 square, right? So we'll do one problem. We'll get the solution of this concept of ionic strength. Okay, right. One problem will be there. This is the problem, right? So that is, find the ionic strength of 0.2 molar of KCl solution. Find the ionic strength of 0.2 molar of KCl solution, right? From the given data, KCl is dissociates into the K plus and Cl minus. The concentration of KCl is similar to the concentration of the ions, right? This concentration of ions are also having same concentration as KCl does has, right? So that means 0.2, 0.2. Therefore, now ionic strength equation I is equals to 1 by 2 of The first K plus, we'll discuss about the K plus. C1N1 Z1 square belongs to K plus. C2N2 Z2 square is belongs to Cl minus. Okay. That is 1 by 2 into number of moles of K means here 1 only. So that is the 1. Okay. Right. Concentration of the K plus is 0.2. That is 0.2. Then charge of K plus, that is a plus 1, that is a plus 1 square. Similarly for Cl minus, number of moles is 1, concentration is 0.1, but charge is minus 1 square. Right? So therefore, by simplifying this, we can get the ionic strength, that is the 0.2. Right? 0.2. So will you find out the ionic strength of H2SO4 whose concentration is 0.2. Right? You people may do this, right? H2SO4 is the electrolyte solution. You people have to do. Take the paper and do it. H2SO4, how it will be dissociates. So then you have to find out the ionic strength of H2SO4 whose concentration is 0.5 m. 0.5 molar. Find out the ionic strength of 0.5 molar of H2SO4. So you have to do and explain. Here I am giving some hint. This H2SO4 is dissociates into 2 moles of H plus, 2 moles of H plus, right? And 1 mole of SO4 minus 2. 1 mole of SO4 minus 2. This is the dissociation. Now find out the ionic strength. Find out the ionic strength of 0.5 molar of H2SO4. This H2SO4 is dissociated into 2 moles of H plus and 1 mole of SO4 minus 2. Apply the equation and find out the ionic strength of this solution. As anyone get it? Yes. Anyone can get the answer, just you can post in the chat box. What was the answer? Or otherwise you have to tell orally. Yes. Or you people are there? No one is responding. In the screen itself is there. How the dissociation of KCl will be there. Right. So this is the KCl is dissociation, and how we'll find out this ionic strength of that KCl. This is the procedure will be there. The same procedure you have to apply it for the H2SO4, but whose concentration is 0.5. Yes. You got the answer?
Sir, 1.5.
1.5. Right. What about remaining? Simple. This is the formula. In this formula, you have to substitute all those things. The first belongs to H plus and second belongs to SO4. Right. Anyone getting 1.5? Any others? The ionic strength is the 1.5 is the correct answer. Did you get it? Yeah. Harishankar, you're getting 0.75, not 0.75. It's 1.5. Take it once. Yeah, 1.5. Right? See here. What are the number of moles of H plus? That is the 2. Here is the 2. Right? Here is the 2. The concentration is 0.1. And the charge is the plus 1 whole square only. 0.5 into 2 means that becomes 1. Bracket law, right? That is in bracket. Plus. What is here number of moles? 1 only. Concentration is 0.5 only. But ion charge is -2. -2 whole square means 4. 4 5 is a 2. 2.0 means that is a 1 plus 2 is the 3. But previous 1 by 2 will be there. 3 by 2 means that is the 1.5. That is the answer of 1.5, right? So, and some other questions I can send to you. You have to do the answer, right? So, some questions I will give to you how to calculate the ionic strength of the various electrolyte solutions like salts, right? So, you have to do some more examples practice, then you will get the idea. Okay, right. So, one more small concept will be there, that is extended d by Haeckel limiting law, right? So what we saw, the Debye-Haeckel limiting law means that is applicable for only weak electrolytes. Debye-Haeckel limiting law, DHLL, is applicable for only weak electrolytes, right? And the equation of Debye-Haeckel limiting law is obtained from the assumptions of Debye-Haeckel theory. Okay. So what is extended Debye-Haeckel limiting law means? In order to apply this Debye-Haeckel limiting law is applicable for the strong electrolytes. Generally, Debye-Haeckel limiting law is applicable for the weak electrolytes only. In order to we apply that simple equation for strong electrolytes, we have to modify some equation. That modified Debye-Haeckel equation is known as extended Debye-Haeckel equation. So this extended Debye-Haeckel equation is applicable for the strong electrolytes. Strong electrolytes. So those strong electrolytes are completely dissociates into the ions, right? That is the thing here. Debye-Haeckel limiting law is applicable for the dilute solutions only. If it is applicable for strong electrolytes by modifying Debye-Haeckel limiting law equation. So whenever a strong electrolyte solutions are there, we have to consider the thickness of the ionic cloud because it's completely dissociates into the ions. Strong electrolytes are completely dissociates into the ions. Therefore, we have to consider the thickness of the ionic cloud. So which is depends on the concentration of the electrolyte solution. The thickness of the ionic cloud is depends on the concentration of the electrolyte solution. For example, as the concentration of an electrolyte solution is increases from 0.001 normality to 0.01 normality, or from 0.001 to 0.1 normality, the ionic cloud is decreases from 100 to 10 angstroms. As the concentration will be increases, the ionic cloud of an electrolyte solution will be decreases. So with the help of these concept, the above equation should be modified and that should be applied for the strong electrolyte solutions also. The modified Debye-Haeckel equation is, right, this is ln gamma plus or minus is equals to minus a z plus z minus into square root of I. Only numerator will be there, that is the Debye-Haeckel limiting law. only numerator will be there, that is d by Haeckel limiting law. Some other terms which will be added to the numerator, that means in the denominator, that is a 1 plus BA into square root of I. So this is what extended d by Haeckel limiting law. A is the size of the ion and B is the mean ionic diameter. With the help of addition of these two, 1 plus BA of square root of I to the d by Haeckel limiting law, so that equation will be modified. Therefore, that becomes extended d by Haeckel limiting law. And also this equation is applicable for the strong electrolyte solutions. Whenever the strong electrolyte solutions are completely dissociates into the ions, even though we apply the concept of d by Haeckel to the strong electrolyte solutions. Strong electrolyte solution. Okay.
Sir, sir,
Yes, yes.
how we will find the size of the ion here, sir, in this equation?
Size of the ion.
Yes, sir. How it can be determined?
This
How we
already
can?
given in the problem only, right? Theoretically, not practically. So the size of the ions means which electrolyte solution we are utilizing. Which electrolyte solution we are utilizing. So that is either univalent electrolyte, that is the HCl is utilizing. So the H plus ion size will be known and Cl minus size will be known. Based on the utilization of the electrolyte solution, whose size is always known, right? The size of the H plus ion is known based on the electronic configuration, that is 1s1, but that one electron also lost, that is the 1s0, right? So the presence of electrons in outermost shell, we can provide the size to the ions. Okay,
Right, sir. Right, sir.
right. So the remaining one more concept will be there, that is the d by Haeckel Ansauger equation, right? So means later Ansauger was added to this d by Haeckel and he derived one equation, that is the d by Haeckel Ansauger equation. The concept of last concept will be there. The concept of this d by Haeckel Ansauger equation that will be discussed in the next class. Okay. So that means complete derivation will be there. It will take some time. After that, theorem theory will be there. Only two concepts will be left. These two will be discussed in the next class. And after that, we'll discuss about the another new chapter, new black, that is the either photochemistry or chemical kinetics. So that will be discussed in the next class. Okay.
Sir,
Yes.
in a brief, sir, can you take one time, sir, thermodynamics, brief, sir. Second, third.
Yes. Some more blacks are there, na? So we have to finish those blacks. After that, if time will be there, we will discuss again thermodynamics.
Yes, sir.
Okay.
Thank you, sir.
Okay. So okay, I am going to conclude the class, right? You have to join in the next your class as per your schedule, right? So take your breakfast and join in the next class. Bye.
Thank you, sir.